There is a particular kind of sentence that modern astronomy keeps forcing us to say. Not because scientists enjoy drama. Not because physics has collapsed overnight. Not because the universe suddenly changed its mind. But because every so often, a telescope looks so far back in time that reality stops behaving like our expectations told us it should. James Webb just detected something that should be impossible. That is the headline version. The disciplined version is stranger. James Webb is finding signs that the early universe may have become bright, structured, chemically mature, and gravitationally organized far faster than many of our models once assumed. Galaxies that seem too luminous. Systems that seem too large. Heavy elements that seem too early. Order where we expected rawness. Maturity where we expected infancy. Not violations of law in the childish sense, but a timeline that may be more aggressive than our theories were prepared for. And that distinction matters. Because, impossible, in astronomy almost never means logically impossible. It means something colder and, in some ways, more unsettling. It means the universe is doing something that does not fit comfortably inside our current expectations for how quickly structure should arise. It means our model of cosmic childhood may have been too timid. It means the deep dark may not be hiding monsters. It may be hiding premature order. That is the real shock. For decades, we told a story about the early universe that felt reasonable. After the Big Bang came cooling. After cooling came the first atoms. After darkness came the first stars. After those first stars came small galaxies, messy galaxies, primitive galaxies. Over long stretches of cosmic time, these systems would merge, grow, enrich themselves with heavy elements, settle into more familiar forms, and gradually become the majestic structures we know today. It was not a foolish story. It was a scientific one. But science is always waiting for the next better instrument to expose where its confidence became too comfortable. And James Webb was built precisely for that kind of exposure. It does not simply see farther than Hubble in the ordinary sense. It sees earlier. Deeper. Redder. It sees light that has been stretched by expansion so severely that the visible universe hands its oldest surviving messages to us in infrared. Webb looks into deep space, yes. But deep space is also deep time. And what it has found there is forcing a difficult question. What if the young universe was not as young as we thought? What if, only a few 100 million years after the Big Bang, some regions of the cosmos were already producing galaxies that looked too bright, too substantial, too chemically processed, too ordered to fit neatly into the old script? What if impossible does not mean nature broke the rules? What if it means nature matured faster than our rules expected? That possibility should bother you. Because the early universe is not a side chapter in cosmology. It is the place where the terms of everything were set. The pace of star formation, the assembly of galaxies, the timing of reionization, the birth of black holes, the origin of heavy elements, the emergence of large-scale structure, all of it depends on how quickly the cosmos learned to organize itself. And if it learned faster than we thought, then the universe may have been stranger from the beginning than our most careful stories allowed. Tonight, we are going to follow that possibility carefully. Not through hype. Not through fake, physics is broken, theater. And not through the lazy comfort of pretending every tension is either a revolution or an error. We are going to ask what Webb actually found. Why those findings caused such unease. What has already been confirmed. What remains debated. What headlines got wrong. And what the deeper emotional shock really is. Because James Webb may not have found the impossible in the fairy tale sense. But it may have found something more scientifically disturbing. A universe that appears to have grown up too fast. And once you see what that means, the deepest darkness in the sky will stop looking empty. It will start to look impatient. Before we talk about impossible galaxies, impossible chemistry, or impossible order, we need to do something that science documentaries do not always do when they are tempted by big words. We need discipline. The James Webb Space Telescope did not launch into space and immediately overthrow modern cosmology. It did not erase the Big Bang. It did not prove that Einstein was wrong. It did not discover one single object labeled impossible in some pure and final sense. What it did was more interesting. It began returning data from epochs of cosmic history that had previously been much harder to examine directly. And in those epochs, especially the era known as cosmic dawn, when the first stars and galaxies were forming, it found multiple classes of objects and signatures that appeared earlier, brighter, more massive, or more mature than many astronomers had expected based on pre-Webb models. That is the real story. And the real story is powerful precisely because it is not one anomaly. It is a pattern. A pattern of early brightness. A pattern of rapid assembly. A pattern of unexpectedly mature chemistry. A pattern of structure emerging where we expected more chaos. A pattern that keeps whispering the same uncomfortable thing. Maybe the early universe was not primitive for very long. Now, some of those early whispers turned out to need correction. Photometric estimates can overshoot. Red colors can be misleading. Some candidate galaxies initially thought to be monstrous at impossible distances became less extreme after better analysis or spectroscopic confirmation. That is how science is supposed to work. The first pass is not the final pass. Webb did not just generate cosmic surprises, it also generated a new reminder that observations require patience. But even after caution, revision, and hard analysis, the deeper challenge remains. The early universe keeps looking less childlike than expected. That phrase matters more than almost any headline. Because headlines love rupture. They want science to be either triumph or collapse. Either everything is fine or everything is broken. But real cosmology lives in a harder, more beautiful region between those extremes. It lives in the zone where the data say, your basic framework may still be right, but your assumptions about pace, efficiency, and timing may have been too conservative. That is what Webb is doing. It is not finding magic. It is finding speed. And speed, in the early universe, changes everything. If stars formed more efficiently, then galaxies could brighten faster. If early stellar populations were more massive, then heavy elements could appear sooner. If gas cooled and condensed more aggressively, then structure could organize itself earlier. If black hole seeds formed rapidly, then luminous active systems could turn on sooner. If our interpretation of the earliest light was too simplistic, then cosmic dawn was always more complicated than the story we got used to telling. The result is not a broken universe. It is a more ambitious one. A universe that may have front-loaded complexity. A universe that may have assembled visible order with unnerving impatience. A universe that may have become legible before we thought legibility was available. And that last point is philosophical as much as scientific. Because hidden inside the Webb story is a deeper emotional shock. We have a habit of imagining origins as crude. We imagine the beginning of something as dim, rough, unfinished, embryonic. We expect adolescence to come later. But what Webb keeps suggesting is that the cosmos may have accelerated through some of its earliest developmental stages much faster than our mental imagery allowed. The impossible may really mean the universe grew up too fast. So that is the journey ahead. We will begin with the machine itself, why Webb changed the search for origins. Then we will move into deep time, redshift, cosmic dawn, unexpectedly bright galaxies, spectroscopy, early oxygen, early dust, reionization, rotating disks, theoretical tension, and the discipline of separating established fact from speculative overreach. And by the end, we will arrive at the deepest question of all. Not whether Webb found an impossible object, but whether it found an impossible timeline. There are telescopes that extend vision. And then there are telescopes that change what vision means. James Webb belongs to the second category. To understand why, we need to let go of the idea that it is simply Hubble, but better. That phrase is useful for marketing and almost useless for understanding. Hubble transformed astronomy by giving us extraordinary optical and ultraviolet views of the universe above Earth's atmosphere. Webb was designed for a different kind of confrontation, a confrontation with origins. Its segmented gold mirror, enormous sun shield, and infrared instruments were built around a particular reality of cosmology. The deeper you look into the universe, the more the expansion of space stretches ancient light into longer wavelengths. The earliest galaxies do not present themselves to us in the clean visible light we might prefer. Their light has been redshifted, pulled toward the infrared by the expansion of the universe over billions of years. This is why Webb had to be cold. Why it had to live far from Earth at the Sun, Earth L2 point. Why it needed a sun shield the size of a tennis court. Why its engineering looked almost absurdly delicate. It was built to catch ancient whispers that visible light telescopes would miss or only partly perceive. In that sense, Webb is not merely a bigger eye. It is an eye tuned to the afterlife of early light. And once you understand that, the shock of its discoveries becomes easier to feel. Webb was not looking randomly. It was aimed at one of the most consequential frontiers in science, the period when the universe began making the first luminous structures. The first stars. The first galaxies. The first systems capable of altering the cosmic environment around them. Before Webb, we had powerful theories and some observational constraints. Hubble had pushed astonishingly far. Ground-based telescopes, gravitational lensing, and simulations gave us a growing picture of how the early universe might have looked. But there was still a difference between inference and direct scrutiny. Webb was built to narrow that difference. What it offered was not simply sharper images, though it certainly delivered those. It offered access to epochs of cosmic history that had mostly lived as models, hints, and extrapolations. It gave us a chance to stop imagining cosmic dawn from a distance and start observing it in detail. And that is exactly why it became dangerous. Because every time astronomy improves its reach into the young universe, one of two things happens. Either the old expectations survive contact with better data and become stronger, or the data arrive with a different personality than expected. Not enough to erase the framework, perhaps, but enough to expose where the framework leaned too heavily on assumptions it could not yet test. That second possibility is where Webb lives now. It is not simply showing us more of the same. It is turning what used to be extrapolation into confrontation. Before Webb, the earliest galaxies were often pictured as tiny, irregular, low-mass, relatively primitive systems assembling themselves slowly in the wake of the Big Bang. Not empty, not featureless, but young in a way we thought we understood. They were supposed to be the rough drafts of later grandeur. Webb began revealing that some of those rough drafts may already have been far more developed than expected. That is why this telescope matters so much emotionally. It does not just take beautiful pictures. It changes the age at which the universe is allowed to surprise us. There is something almost intimate about that. Humanity spent centuries looking at stars and then decades building the instruments required to look back toward the first chapters of galactic history. And once we finally built the right machine, the young universe did not greet us as a simple cradle. It greeted us with tension. Too bright. Too fast. Too mature. Too organized. Or at least, that was the first impression. And first impressions in astronomy can be treacherous. They can be thrilling, misleading, or both. So before we start believing every claim about impossible galaxies, we need to understand the key trick that makes Webb's observations so powerful in the first place. Deep space is not just far away. It is long ago. One of the most beautiful and unsettling facts in astronomy is that looking far away is a form of time travel. Not the science fiction kind. Not backward travel for the observer. Not a violation of causality. Something stranger and more real. Light takes time to move. That sounds obvious, but obvious facts can become metaphysical when the scale becomes cosmic. The sun we see is 8 minutes old. The nearest star, apart from the sun, is seen years in the past. Distant galaxies appear not as they are now, in some universal sense, but as they were when their light began the journey toward us. The farther we look, the older the message. This means astronomy is not merely the study of remote objects. It is the archaeology of delayed visibility. When Webb stares into the deep universe, it is not simply extending distance. It is entering earlier eras of cosmic history. It is looking toward a time when the universe was young enough that galaxies were just beginning to assemble, stars were just beginning to ignite in large numbers, and the cosmic environment itself was changing from darkness to luminous structure. But because the universe has been expanding during all that time, the story is not as simple as far equals old. The light we receive from the earliest galaxies has not traveled through static space like a bullet crossing a room. Space itself has stretched while the light was in transit. That stretching increases the wavelength of the light, shifting it toward the red and eventually into the infrared. This is what redshift measures. A high redshift object is not merely moving away in the everyday sense. It is embedded in the expansion history of the universe itself. The greater the redshift, the more the light has been stretched, and generally the earlier in cosmic history we are seeing the object. That is why infrared astronomy is so powerful for origins. The first luminous structures in the universe are not hidden because they emitted nothing. They are hidden because their light has been transformed by cosmic expansion into wavelengths a telescope like Hubble could only partly reach, while Webb was specifically engineered to follow. There is something conceptually profound here. The young universe does not vanish behind us in time. It remains all around us, carried in ancient photons. Cosmic history is still arriving. That fact alone makes astronomy feel almost supernatural, but it is fully physical. The sky is not only a map of place. It is a layered archive of when. And once you understand that, the Webb story becomes much more than a story about distant galaxies. It becomes a story about whether the archive of the universe tells a different developmental history than we expected. Because if we expected the first few 100 million years to be dominated by dim, sparse, chemically primitive systems, and instead we find objects that seem surprisingly bright, chemically active, or structurally organized, then the problem is not just classification. The problem is chronology. Did things happen sooner? Did they happen faster? Did they happen more efficiently? Did the young universe use its available time more aggressively than we thought? These are dangerous questions because cosmic dawn is not a decorative era. It sets the tone for everything that follows. The pace of early star formation affects reionization. Early black hole growth affects galaxy evolution. Early enrichment with heavy elements changes how subsequent generations of stars and planets can form. Early morphology changes our picture of how order emerges from initial conditions. In other words, the first few 100 million years are not just an introduction. They are a test of whether our entire story of cosmic maturation has the right tempo. And that is why deep space has such emotional weight in the Webb era. We are not merely looking farther. We are auditing the beginning. To do that properly, though, we need to understand what astronomers thought they were going to find before Webb made the young universe feel unexpectedly ambitious. We need to visit cosmic dawn as expectation, before we revisit it as evidence. Before James Webb began returning its most provocative data, the broad story of cosmic dawn was already one of the great narratives of modern cosmology. It began with the Big Bang, the hot, dense early state of the universe. After expansion and cooling came recombination, when electrons and protons combined into neutral atoms and the universe became transparent to radiation, leaving behind the cosmic microwave background. Then came the cosmic dark ages, a period after that first light was released but before stars had fully ignited in large numbers. Eventually gravity did what gravity always does. It took tiny fluctuations in density and amplified them. Slightly denser regions pulled in more matter. Dark matter halos formed. Gas fell into those potential wells, cooled, and under the right conditions made the first stars. Those stars, in turn, began the long work of transforming the universe, producing ultraviolet light, forging heavier elements, exploding, seeding new generations of stars, and contributing to the process of reionization, in which neutral hydrogen throughout the cosmos became ionized again. That broad picture remains intact. What was more uncertain, and still is, was the pace. How quickly did the first stars form? How efficiently did gas turn into starlight? How soon did galaxies reach significant mass? How early did heavy elements and dust appear? How messy or organized were the first galactic systems? How fast did luminous sources carve clear regions in the surrounding fog of hydrogen? Before Webb, many models suggested caution. Not because astronomers thought the early universe was dull, but because the basic constraints seemed to imply limited time. When you are only a few 100 million years after the Big Bang, there has simply not been much opportunity, in ordinary intuition, to build large and mature systems. Small clumpy galaxies? Yes. Patchy star formation? Yes. Primitive structures? Certainly. But massive, unusually bright, chemically evolved, and perhaps even dynamically organized systems? Those were expected to be rarer, later, or at least less obvious. Again, this was not dogma. It was a reasoned expectation shaped by simulations, earlier observations, and the known difficulties of cooling gas, forming stars, generating feedback, and building large structures in a young universe. The young universe was supposed to look young. That is the expectation Webb began to disturb. Because one of the earliest shocks was not simply that Webb could see galaxies farther back. It was that some of them appeared brighter and more substantial than many people were prepared for. Instead of a quiet infancy, some fields seemed to contain objects that looked almost startlingly grown up. Now, this is where science needs discipline, because appeared does important work in that sentence. In early Webb data, photometric estimates can make some candidates look more extreme than they later prove to be after spectroscopic confirmation, revised modeling, or improved treatment of dust and stellar populations. The history of astronomy is full of first impressions later made more ordinary. But, more ordinary, in this case has not meant fully ordinary. Even after the first wave of recalibration, Webb's early universe findings still keep pointing in the same direction. The first luminous systems may have assembled faster, or shone more efficiently, or converted baryons into stars more aggressively, or matured chemically more rapidly than many pre-Webb expectations allowed. That is why cosmic dawn became so psychologically unstable after Webb. Not because everything we expected vanished, but because the range of what the early universe seemed capable of widened. It became harder to picture those first few 100 million years as a timid prelude. They began to look more like a compressed era of ferocious growth. And that matters because astronomy does not merely want to know what is out there. It wants to know how quickly complexity becomes possible. The early universe is where we test that limit. How long does it take for darkness to become structure? How long does it take for chemistry to become non-trivial? How long does it take for gravity to produce recognizable order? How long does it take for light to begin changing the universe around it? Webb is suggesting the answer may be, not as long as we thought. Which brings us to the discovery category that triggered the loudest headlines. Galaxies that seemed too bright, too massive, too soon. There is a very specific kind of scientific unease that appears when an object is not merely surprising, but chronologically rude. It is the feeling that something has arrived before the script was ready for it. That is what happened when some of Webb's earliest deep-field observations seemed to reveal galaxies in the young universe that were brighter, and in some interpretations more massive, than many models had predicted for such early times. The phrase, impossible galaxy, began circulating almost immediately. It is a bad phrase. But it points at a real tension. If a galaxy exists when the universe is only a few 100 million years old, then its stars had limited time to form. Its gas had limited time to cool and collapse. Its host halo had limited time to gather mass. If multiple such systems appear surprisingly bright or abundant, then the issue is no longer one peculiar outlier. It becomes a question about formation efficiency and the tempo of structure growth. In some early Webb analyses, candidate galaxies at very high redshift looked astonishingly luminous. That luminosity, under certain modeling assumptions, suggested large stellar masses had already accumulated shockingly early, in some cases making these objects seem uncomfortably mature relative to standard expectations. The immediate public reaction was predictable. Cosmology is broken. The Big Bang is wrong. The early universe should not contain these things. But the real scientific reaction was more careful and, in my view, more intellectually dramatic. Maybe our assumptions about how early galaxies shine are incomplete. Maybe their stellar populations differ from later galaxies. Maybe they are producing light more efficiently. Maybe strong emission lines or dust effects are changing our inferences. Maybe some mass estimates are too high. Maybe spectroscopy will revise the distances. Maybe the galaxies are still real, still early, and still surprising, just not apocalyptic. This is how mature science responds when the sky misbehaves. Not by panicking. By interrogating the inference chain. And that chain is complicated. Brightness is not mass. Red color is not age in any simple one-step sense. Photometric redshifts can be impressive but need confirmation. Young stellar populations with unusual properties can look misleadingly mature under simplified assumptions. Strong nebular emission can contaminate certain bands and reshape what we infer from them. So yes, some of the most explosive early claims softened with time. But softness is not the same as disappearance. Even after refinement, the young universe still seemed crowded with systems that were surprisingly luminous, sometimes surprisingly evolved, and not easily aligned with the most conservative pre-Webb expectations. The issue was not that every candidate remained monstrous. It was that the pattern of early brightness kept recurring often enough to feel structurally meaningful. That is when a deeper possibility emerged. Maybe the early universe was not violating cosmology. Maybe it was using cosmology more efficiently than we had assumed. That is a less cinematic explanation than everything is wrong, but it may be more revolutionary in practice. Because once you admit that early star formation, early feedback, or early baryon conversion efficiencies may have been systematically underestimated, the whole developmental profile of cosmic dawn changes. Galaxies stop looking impossible and start looking rapid. The problem shifts from logical contradiction to underestimated ambition. And that shift has consequences. If galaxies formed stars faster, then reionization may have been driven differently than expected. If early systems were brighter for their mass, then our census of cosmic dawn changes. If halos hosted luminous galaxies sooner, then merger histories, black hole seeds, and chemical evolution all need recalibration. If our intuition about infancy was too slow, then the whole emotional picture of the young universe changes with it. This is the motif that Webb keeps returning to. Not monsters. Premature order. The impossible may really mean that the universe assembled visible complexity with unnerving speed. Still, brightness alone is slippery. A red and luminous object does not automatically mean an old and massive object. Sometimes the debate turns not on what is seen, but on how that light is interpreted. So now we have to confront one of the subtler parts of the Webb story. Why red does not always mean old. And why it still shook the field anyway. One of the easiest mistakes in early universe astronomy is to treat color like a confession. This object is red. Therefore it must be old. This galaxy looks bright and red. Therefore it must already contain an ancient, mature stellar population. This system seems chemically evolved. Therefore it must have been around much longer than the age of the universe permits. Sometimes that logic works. Sometimes it does not. The problem is that color, especially in the distant universe, is never just one thing. Light from a remote galaxy arrives filtered through expansion, redshift, dust, stellar population effects, emission lines, and instrument response. A red appearance can mean age. It can also mean dust. It can reflect strong line emission. It can be shaped by unusual stellar populations. It can be transformed by the enormous redshifting of the universe itself. So when Webb began finding red and luminous sources in the young cosmos, astronomers had to resist the most dramatic interpretation, at least initially. Some of the first claims about impossibly massive early galaxies depended on fitting the observed light with models that treated the redness as evidence of mature stellar populations and therefore substantial stellar mass. But if those models overestimated age, or missed line contamination, or assumed the wrong underlying population, then the masses might come down. The objects might remain extraordinary while becoming less cosmologically scandalous. This is exactly why astronomy is harder than headlines. A telescope does not hand you a galaxy's biography. It hands you photons. The biography has to be inferred. And inference, in the early universe, is dangerous because the systems you are observing may not resemble the later systems on which your interpretive habits were trained. That last point is crucial. One reason Webb has destabilized early universe thinking is not simply that it found distant objects. It found objects in regimes where our expectations about stellar populations, dust formation, ionizing radiation, and star formation histories may have been too anchored to later cosmic eras. The early universe may have had its own lighting conditions, its own efficiencies, its own shortcuts to brightness. So yes, red does not always mean old. But that does not rescue everything into comfort. In some ways, it makes the story stranger. Because if some of these objects were not impossibly old but instead unusually efficient at producing light, then the early universe was not calmer than expected. It was more intense. That is not a reduction of tension. It is a redistribution of it. Instead of saying, these galaxies are impossibly mature, we say, these galaxies may be producing an extraordinary amount of light for their age and mass. Instead of one problem, we inherit another. How? Why? Under what physical conditions? With what kinds of stars? Under what feedback regime? With what baryon-to-star conversion efficiency? Either way, cosmic dawn becomes more aggressive. This is one reason the Webb era feels scientifically honest in a way that is emotionally unsatisfying. The story keeps refusing to collapse into one neat conclusion. Some objects really are less extreme than first advertised. Some estimates do get revised. Some claims do soften. Yet the bigger pattern of unease remains because the revisions often transform one surprise into another rather than eliminating the surprise altogether. In that sense, Webb is teaching the public an advanced lesson in how science actually works. The raw headline says impossible. The careful analysis says complicated. The mature conclusion says the timeline may still be under strain, just not for the exact first reason you thought. And that is where distance confirmation becomes decisive. If you want to know whether a galaxy is truly ancient rather than merely odd-looking, you need more than suggestive colors. You need spectroscopy. You need the discipline of confirmation. A beautiful image can start a scientific argument. A spectrum can end one. Or at least refine it enough that the real argument can finally begin. This is why spectroscopy matters so much in the Webb story. Imaging can reveal extraordinary candidates, faint smudges, red points, luminous patches whose colors suggest extreme redshift and therefore extreme age. But color alone is not enough. If you want to know how far away an object really is, what elements are present, how fast gas is moving, and what physical processes may be shaping the light, you need to spread that light out and read its fingerprints. That is what spectroscopy does. Each chemical element leaves distinctive features in emitted or absorbed light. Because the universe is expanding, those features are shifted toward longer wavelengths. Measure that shift correctly, and you gain a much more reliable handle on redshift than broad color alone can provide. You also gain access to diagnostics of star formation, ionization, metallicity, and internal conditions. In other words, spectroscopy turns the sky from a painting into a document. And in the context of Webb, it has been essential for separating genuine early universe shocks from overexcited first impressions. This is where the public narrative often loses patience. The first image arrives, the headlines ignite, and then months later a more careful paper explains that the object is still fascinating but perhaps not the apocalypse some people wanted. To non-specialists, that can sound like backpedaling. To science, it is exactly the process of becoming honest. The early universe is a hard witness. Its light is faint, stretched, and often ambiguous. Some sources that look like ancient galaxies can turn out to be lower redshift interlopers, dusty systems, or objects whose inferred properties change substantially after better analysis. This has happened before Webb, during Webb, and will happen again. But here is the crucial point. The need for confirmation does not weaken the Webb revolution. It defines it. Because the most scientifically meaningful thing about the Webb era is not that every first claim survives intact. It is that enough confirmed high redshift objects survive the scrutiny to keep reshaping the debate. Take the earliest confirmed galaxies. Once spectroscopy locks in a high redshift, the philosophical temperature changes. You are no longer arguing over whether the object merely looked ancient. You are confronting the fact that it really existed in a universe only a few 100 million years old. The argument then shifts from distance to interpretation. How bright was it intrinsically? How much stellar mass did it likely contain? How chemically evolved was it? What kind of stars powered it? How representative is it of its epoch? That is a much deeper argument. It is one thing to say, our candidates might not be that far away. It is another to say, they really were that early, and now we need to explain how they became what they were. Spectroscopy has also intensified the story by confirming not just redshift, but chemistry. When heavy elements such as oxygen appear in extremely early systems, or when the signatures of energetic radiation environments show up sooner than expected, the problem ceases to be simple photometric misclassification. It becomes a question about how quickly stars lived, died, enriched their surroundings, and reshaped subsequent generations. This is why the Webb story is not just about seeing farther. It is about reading deeper. A telescope image can make you gasp. A spectrum can make you revise history. And what the spectra have increasingly suggested is that some early galaxies were not merely present. They were busy. They had already been making stars. Already processing gas. Already changing their environments. Already participating in a cosmic ecosystem that, until recently, we imagined as younger and more tentative than this. Deep space may be hiding not violations of law but a timeline more aggressive than our theories expected. That is perhaps the most Webb sentence possible. But if the pace of structure formation is the first shock, the pace of chemistry may be even more intimate. Because brightness can be reinterpreted. Color can mislead. Mass can be recalculated. Heavy elements are harder to wave away. If oxygen and dust are there early, something has already lived and died. Something has already been happening. There is a profound difference between seeing light and seeing history. Heavy elements are history. Hydrogen and helium came first in abundance. The universe began chemically simple. The richer elements, carbon, oxygen, silicon, iron, and the rest of the periodic drama that eventually makes planets, oceans, atmospheres, and people, had to be forged later, mainly in stars and in the violent deaths of stars. That means whenever we detect significant chemical maturity in a remote galaxy, we are not just seeing a luminous object. We are seeing generations. Stars had to form. Stars had to evolve. Some had to die. Their products had to spread into surrounding gas. New structure had to inherit the consequences. That is why early oxygen detections and early dust signatures in very distant galaxies felt so startling. These were not merely the first sparks in pristine gas. They were signs that the machinery of stellar life cycles had already been operating quickly enough to enrich the young universe sooner than many expected. It was like finding the chemical handwriting of adolescence in a universe we had mentally labeled newborn. Again, careful language matters. Early does not mean impossible. Surprising oxygen does not mean cosmology collapses. Dust at high redshift does not mean the Big Bang was wrong. But it does mean that some regions of the young cosmos may have burned through their developmental stages with astonishing urgency. This is especially striking because dust formation is not trivial. Dust is a byproduct of heavy element production and processing in stars and stellar explosions, and it affects almost everything. It changes how galaxies emit and absorb light. It influences cooling. It shapes how we interpret observed brightness and color. A dusty galaxy is a galaxy with prior history. So when Webb and companion observations reveal early chemical maturity, the story becomes harder to tell as a simple tale of first light emerging from untouched primordial gas. Instead, we start seeing evidence for rapid recycling. Matter is not just forming stars. It is already being transformed, enriched, and reused. The universe appears to have become chemically conversational sooner than expected. That phrase may sound poetic, but it is physically exact in spirit. A chemically primitive universe is one where matter is largely still speaking in first-generation terms. A chemically enriched universe is one where stars have already begun leaving complex messages for the next generation. Oxygen means the first stars were not just there. They were consequential. And the earlier that consequence appears, the less time there is for cosmic innocence. This is where Webb's discoveries become emotionally destabilizing in a way the mass debate alone does not capture. A galaxy that is merely bright could, in principle, be explained by efficient star formation under special conditions. But a galaxy showing signs of substantial chemical evolution is harder to keep mentally young. It implies lived time inside cosmic time. Internal history inside apparent infancy. The early universe keeps looking less primitive than expected. That is the line chemistry writes across Webb's data. And chemistry does not merely tell us that stars existed. It tells us those stars interacted with the larger environment, which leads directly to one of the biggest epochal transitions in cosmic history. Reionization. Because once enough luminous sources turn on, the universe does not remain the same. It becomes clearer, more transparent, more exposed. And Webb has complicated that story too. There was a time when the universe was full of fog. Not fog like weather. Fog like neutral hydrogen. After recombination, the universe became transparent enough for the cosmic microwave background to travel freely. But much later, before large populations of stars and galaxies had fully transformed the cosmic medium, intergalactic space still contained neutral hydrogen capable of absorbing certain kinds of ultraviolet light. This created a kind of opacity in the early universe. Then came reionization, the era when the first luminous sources produced enough energetic radiation to ionize much of that neutral gas. This is one of the great transitions in cosmic history. It is the moment when the universe became more permeable to light from galaxies. More legible. More exposed. More connected, in a radiative sense, to its own emerging structure. Naturally, this process depends on timing. How early did significant luminous sources appear? How efficient were they at producing ionizing photons? How patchy was reionization? How quickly did ionized bubbles grow around young galaxies? What kinds of sources dominated? Ordinary star-forming galaxies, unusually massive stars, active galactic nuclei, or some combination? Webb has not answered all of that cleanly. But it has made the questions feel hotter. Some early detections, including unexpectedly clear signatures in objects seen only a few 100 million years after the Big Bang, have suggested that parts of the universe may have become transparent or locally cleared sooner than many people expected. That does not mean reionization was finished absurdly early everywhere. The process was likely patchy and extended. But it does imply that some sources were already doing strong environmental work very early on. The young universe was not merely producing light. It was editing its own fog. That is a powerful image because it turns cosmic dawn from a passive epoch into an active one. These first galaxies were not just ornaments turning on in a dark backdrop. They were agents in a phase transition. They were reshaping the medium through which later light would travel. And when Webb detects surprisingly strong or early signatures associated with these processes, the deeper question returns once more. How did the universe get this capable this fast? If some early galaxies were already carving ionized regions into the surrounding hydrogen, then they were not minor actors. They were cosmological infrastructure. Their light mattered to the state of the universe around them. That means early star formation was not just a local curiosity. It was a global force. There is something philosophically beautiful about this. The young universe is often imagined as a dark passive place waiting for structure to eventually become interesting. But reionization tells a different story. The first luminous systems were not merely small beginnings. They were transformative enough to change the transparency of the cosmos. Webb has made that transformation feel less gentle than we imagined. Not necessarily instantaneous. Not magic. But intense. And again, this is where people can overstate the case. A few striking early objects do not rewrite the full global timeline by themselves. Selection effects matter. Confirmation matters. Reionization remains an active research frontier with large uncertainties. But what Webb has done is force greater seriousness about the possibility that the relevant sources were efficient, powerful, and perhaps surprisingly common early on. In other words, the young universe may not have been groping its way toward clarity. It may have been driving toward it. That brings us to one of the most visually disturbing themes in Webb's observations. Not just brightness. Not just chemistry. But structure itself. Because even if the early universe formed stars quickly, we still expected some of its systems to look messy for a long time. And yet hints of surprisingly ordered, disk-like, rotationally coherent galaxies have begun appearing much earlier than many people were comfortable with. The problem is no longer just that the universe lit up fast. It may have organized fast too. Chaos is one of the comforts we grant to beginnings. We expect infancy to be clumsy. We expect early structure to be irregular, fragmented, and unsettled. In cosmic terms, we expect the first galaxies to look more like rough assemblies than like the graceful, rotating, organized systems that later populate the universe. This expectation was not arbitrary. Young galaxies in the early universe should, in many scenarios, be rapidly accreting gas, merging, forming stars violently, and living in a dense environment where stability is hard-won. Order was expected to emerge eventually, but not too quickly. Then observations began hinting that some early systems may have been more organized than that. Disk-like structures. Rotation-dominated behavior. Unexpectedly orderly morphology. Now, caution matters here more than almost anywhere else in the Webb story. Morphology at great distance is treacherous. Resolution, orientation, dust, clumpiness, lensing, and interpretation all matter. A single image can tempt the eye into seeing familiar order where the data only partially justify it. Likewise, kinematic inferences require care. To say a galaxy is truly rotation-dominated is stronger than saying it merely looks flattened or suggestively structured. But once again, the point is not that one perfect impossible spiral was found and all doubt ended. The point is that multiple observations, from Webb and from facilities like ALMA, have begun strengthening a broader suspicion: some galaxies in the early universe may have settled into organized dynamical behavior earlier than many pre-Webb instincts expected. That is deeply important. Because a galaxy is not just a pile of stars. It is a history of angular momentum, gas inflow, cooling, feedback, turbulence, and gravitational negotiation. Orderly rotation means something survived those negotiations long enough to become legible. It means the early universe may have produced not just luminous systems, but systems with structure stable enough to look familiar. That familiarity is what makes the discovery so eerie. A disk galaxy in the very distant universe does not look like an alien object. It looks like something we thought belonged to a later chapter. It is not the shock of radical difference. It is the shock of premature resemblance. The universe may have learned some of its later tricks absurdly early. And that shifts the emotional center of the Webb story. The problem is no longer only, how did galaxies get so big so soon? It becomes, how did galaxies become recognizable so soon? That question is harder to dramatize for the public but far more profound for cosmology. Brightness can be transient. A burst of star formation can light up a system dramatically. But order implies organization across time. It suggests that some deep processes, angular momentum transport, gas settling, disk assembly, feedback regulation, may have converged faster than we thought the universe could manage. Again, not impossible in the literal sense. But chronologically offensive. The impossible may really mean that the universe was better at becoming itself than we imagined. And now the central tension can no longer be avoided. Did Webb actually break cosmology? Or did it expose how much of pre-Webb confidence rested on fragile assumptions about efficiency, timelines, and what early was allowed to look like? Whenever a new instrument reveals tension between observation and expectation, the public instinct is to ask the biggest question immediately. Is the whole theory wrong? Sometimes the answer is yes. More often, the answer is subtler. Not because science is timid, but because large frameworks usually do not fail all at once. They fail at their margins first, in parameters, assumptions, scaling laws, or hidden simplifications. The core structure survives while the details get dragged into a brighter and more honest light. That appears to be the Webb situation. The standard cosmological model is not collapsing because early galaxies are bright. The expansion of the universe, the cosmic microwave background, primordial nucleosynthesis, gravitational structure formation, dark matter, and the broad timeline of cosmic evolution still fit an enormous body of data. Webb has not made those pillars disappear. What it has done is reveal that the path from the early universe to the visible galaxy population may have been modeled too conservatively in important ways. This distinction is everything. If you say, Webb broke cosmology, you make the problem sound like a theatrical duel between telescope and theory. But the real story is more scientifically rich. Webb has exposed how much our story of cosmic dawn depended on assumptions about star formation efficiency, stellar population properties, dust production, feedback, merger rates, baryon conversion, and observational selection. In other words, it has exposed fragility in the developmental model, not necessarily in the existence of the universe's overall framework. And perhaps that should have been expected. The early universe is exactly where simple assumptions are most dangerous. Conditions were more extreme. Gas fractions were higher. Environments were denser. Radiation fields were harsher. The first generations of stars may not have resembled later ones. Feedback may have operated differently. Black holes may have seeded or grown under conditions we still poorly understand. Why should we have expected familiar rates under unfamiliar conditions? This is the question Webb keeps asking. Not, were the laws of physics false? But, why did you think the young universe would use them so slowly? That is a devastatingly elegant way to put it. Because it turns the discomfort back onto theory in exactly the right place. The problem may not be the laws. The problem may be our instincts about what those laws allow under early conditions. This is not a downgrade of the Webb revolution. It is the revolution. A telescope does not need to kill a theory to transform a field. Sometimes it is more important for a telescope to expose the hidden laziness in how the theory was being applied. It can reveal where simulations underexplored certain efficiencies, where priors became habits, where one picture of infancy hardened into dogma without enough direct evidence. That is how science advances most honestly. Still, we should not minimize the tension. If enough confirmed high redshift galaxies remain brighter and more chemically evolved than expected, if enough early systems show surprising structure, if reionization appears to demand more early luminous output, then the model-building challenge is serious. Not sensationally apocalyptic, but serious. The early universe becomes a harder place to simulate and a less comfortable place to extrapolate into. And that means the Webb era is forcing a re-education of imagination. Cosmic dawn may have been less like dawn in the poetic sense, dim, gradual, hesitant, and more like a sudden and aggressive ignition of structure. That is what destabilizes people. Not because it kills cosmology. Because it changes the temperament of the beginning. And once we begin changing that temperament, one idea rises to the center of the explanation space more than any other. Maybe the early universe made stars faster than we thought. Maybe that one sentence, expanded properly, is enough to account for much of the unease. There is a temptation in astronomy to treat galaxies as if they merely accumulate. But galaxies also convert. They take gas and, under the right conditions, convert some of it into starlight. How efficiently they do this is one of the deepest questions in galaxy formation. Too little efficiency, and structures remain dim and undergrown. Too much, and the early universe lights up faster than expected. Webb has made the second possibility much harder to ignore. If many of the surprising observations can be reconciled without overthrowing cosmology, one of the most attractive routes is that star formation in some early systems was more intense, more efficient, or populated by stars that emitted light differently than many pre-Webb assumptions allowed. Perhaps the first galaxies turned available gas into luminous stellar populations more aggressively. Perhaps early stellar initial mass functions were biased toward more massive stars. Perhaps nebular emission contributed strongly. Perhaps low metallicity conditions created stellar populations that shone with unusual effectiveness. These are not desperate excuses. They are physically motivated possibilities. And they all point in the same direction. The early universe may have been better at becoming visible. That is a profound thought. We often imagine the first galaxies as dim, hesitant lanterns in a hostile dark. But maybe some were not hesitant at all. Maybe they were fierce conversion engines, turning young gas into ionizing light and heavy elements with a pace that later cosmic environments rarely matched. This would help explain several things at once. Brighter galaxies at early times. More rapid contribution to reionization. Earlier enrichment with oxygen and dust. Apparent maturity without needing every system to be impossibly massive. It would also shift the emotional meaning of cosmic dawn. Instead of a slow and mostly invisible prelude, it becomes a compressed era of astrophysical ambition. Gas collapses. Massive stars ignite. Radiation tears into surrounding hydrogen. Supernovae enrich the medium. Subsequent star formation inherits altered conditions. Within a cosmically short interval, the universe starts looking less like an infant and more like a fast-learning adolescent. There is an irony here that I find beautiful. For years, some people spoke of the early universe as if it were inaccessible because it was too simple. Webb is showing that it may be inaccessible because it was already too complicated. That is a different kind of mystery. Now, star formation is not the whole answer. Dark matter halos matter. Gas accretion matters. Feedback matters. Black hole growth may matter. The initial conditions matter. The interaction between these components is messy and model-dependent. But if Webb is exposing one large blind spot in pre-existing imagination, it is probably this: we may have underestimated how aggressively the earliest cosmic structures could manufacture luminosity. And once again, that does not mean the universe violated its laws. It means the timeline may have been more front-loaded than our habits allowed. There is something philosophically striking about that. We like to imagine complexity as patient. We imagine it needing long eras, long negotiations, long evolutionary spirals to become visible. But the cosmos may not share that instinct. Under the right physical conditions, it may rush. It may use available gradients with shocking boldness. It may produce organized brightness before we are ready to grant it permission. Deep space may be hiding not violations of law but a timeline more aggressive than our theories expected. By now that line should feel less like poetry and more like diagnosis. Still, to really understand what the public keeps getting wrong about Webb, we need to confront the headline word directly. Impossible. What does that word mean in real science? And what does it not mean? Science does not use the word impossible the way the internet does. That is one of the first things Webb has taught the public, even if many people refuse the lesson. In everyday speech, impossible means absolutely ruled out. Contradictory. Nonsensical. Forbidden by logic or law. In astronomy, impossible often means something softer and more scientifically dangerous. It means, this observation appears to be in serious tension with prior expectations, standard parameter choices, or common modeling assumptions. That is not as catchy. It is also far more interesting. Because a truly impossible result in science usually does not arrive alone. It collides with multiple independent pillars and forces either a massive rethink or the identification of an error. Most of the time, what people call impossible is instead one of three things. First, an observational misclassification. The object is not what we thought. The distance was wrong. The interpretation was premature. Second, a modeling problem. The object is real, but our assumptions about its underlying physics were too restrictive or too familiar. Third, a sign of deeper tension that may indeed force revision, but not necessarily of the whole framework. Instead, it may revise efficiencies, histories, environments, or the way several processes interact. Webb's early universe findings mostly live in the second and third categories, with occasional examples of the first. That is why responsible scientists do not say, Webb proved the impossible. They say things like, these observations are challenging current models, or these sources appear earlier or brighter than expected, or we may need to revise our understanding of early galaxy formation. It sounds less dramatic because it is more mature. But here is the key point the public often misses. In science, tension is where the real drama lives. Not in clean impossibility. In disciplined discomfort. A completely impossible result can sometimes be dismissed as a mistake until proven otherwise. A result that is merely stubbornly uncomfortable is often more transformative, because it survives. It forces the field to sit with it, adjust around it, and gradually rebuild its assumptions without the catharsis of total revolution. That is the Webb mood exactly. The universe is not handing us absurdity. It is handing us pressure. Pressure on formation timescales. Pressure on star formation efficiencies. Pressure on how early chemistry appears. Pressure on how quickly galaxies can become visible, luminous, and recognizable. This is also why the word impossible still has some legitimate emotional use, even if it is technically sloppy. It captures the sensation of looking at an object and feeling, you should not be this far along yet. That feeling is real. It is just not the same as a theorem. The universe may be doing something our theory technically allows in principle but did not lead us to expect in practice. And that is one of the most fruitful things science can encounter. It is how hidden assumptions get found. We often imagine scientific revolutions as great negations, old ideas smashed by new evidence. More often they are humiliations of confidence. Nature reveals that a framework was pointing in roughly the right direction, but the timetable, efficiency, or texture we confidently attached to it was too simple. Webb may become one of the great instruments of that kind of humiliation. Not because it found magic. Because it found a beginning with sharper teeth than our expectations. The early universe keeps turning out less primitive than expected. At some point, that phrase stops sounding like a summary and starts sounding like the core revelation. Which brings us to a more human way of saying it. Maybe the early universe did not look like a baby. Maybe it looked more like an adolescent. Restless. Fast-growing. Already chemically complicated. Already making itself hard to parent theoretically. When people imagine the early universe, they usually imagine simplicity. Tiny galaxies. Pristine gas. Dim beginnings. A kind of cosmic nursery where almost everything is still in draft form. Webb has not erased that picture completely. But it has made it feel incomplete in a way that is hard to ignore. Because the young universe keeps showing signs not only of beginning, but of acceleration. Not only first-generation light, but rapid development. Not only existence, but signs of prior activity. It is less the quiet innocence of infancy and more the unstable rapidity of adolescence, growth spurts, abrupt chemical change, structural experimentation, and bursts of energy intense enough to transform the environment. That metaphor is not perfect, but it captures something emotionally accurate in the data. A galaxy with surprising oxygen is not a newborn in any meaningful chemical sense. A luminous source participating in reionization is not merely lit, it is consequential. A disk-like or rotation-dominated system is not just present, it is dynamically negotiating order. A field full of surprisingly bright sources is not simply populated, it is evolving at a tempo that makes our old narrative feel too slow. Why does this matter so much? Because infancy is easy to understand. We grant the young universe permission to be crude. We imagine later complexity as an earned reward of time. But adolescence compresses development. It implies that the universe may have entered self-organization sooner than we are emotionally prepared to accept. That changes the philosophical mood of cosmology. The cosmos starts looking less like a patient sculptor and more like an impatient constructor. It wastes less time than we thought. It reaches legibility sooner. It starts leaving chemical fingerprints sooner. It begins altering the intergalactic medium sooner. It may even begin arranging gas into recognizable forms sooner. The impossible may really mean the universe grew up too fast. That line is more than branding. It is the emotional heart of the Webb era. And perhaps this should not surprise us as much as it does. Human beings have a habit of confusing ignorance with simplicity. The early universe was observationally obscure for good reasons. Its light was redshifted, faint, and hard to detect. We often translated that obscurity into conceptual youth. But darkness is not the same as immaturity. Hidden things are not always primitive. Sometimes they are merely distant enough to arrive late in our understanding. Webb has begun correcting that mistake. It has shown that cosmic dawn may have been dark to us while already being internally busy, chemically active, and structurally ambitious. There is a peculiar sadness in that realization. For decades, our mental image of the beginning carried a kind of innocence. The earliest galaxies were supposed to be humble. Instead, they may have been ferocious little factories, turning the first available matter into stars, radiation, and elements as if the universe knew exactly where it wanted to go. Of course, this is still an emerging picture. Not every early galaxy is a mature powerhouse. Not every high redshift detection implies advanced structure. The early universe still contained a range of systems, many of them small, irregular, and truly primitive by later standards. The point is not that infancy vanished entirely. The point is that adolescence arrived sooner than we thought. And that forces a level of scientific honesty we now absolutely need. Because whenever the sky begins behaving like this, two dangers appear immediately. One is exaggeration. The other is denial. So before we enter the emotional implications, we need to draw a clean line. What is firmly established? What is a genuine tension? And what remains speculation riding on the energy of surprise? This is the section every serious cosmic mystery deserves. Not because caution kills wonder, but because it protects wonder from becoming stupidity. So let us separate the Webb story into 3 layers. ##### What is established? James Webb is observing galaxies at extremely high redshift, meaning it is directly probing very early cosmic history. This alone is transformative. It is also well established that some early galaxies are brighter than many pre-Webb expectations would have led people to anticipate. The young universe is not observationally empty. It is producing significant luminous structure early. It is further established that some high redshift systems show signs of non-trivial chemical enrichment, heavy elements such as oxygen, and in some cases evidence consistent with early dust and rapid stellar processing. The earliest luminous systems were not always chemically pristine for long. It is also increasingly supported that some early galaxies may exhibit surprisingly organized morphology or dynamics, though each individual claim requires care and the category remains more nuanced than Internet summaries imply. Finally, Webb has unquestionably intensified the debate over how rapidly reionization proceeded locally and globally, and what kinds of sources drove it. These are not fantasies. They are part of the real observational transformation underway. #### What is genuine tension? How much stellar mass some early galaxies truly contain? How efficiently early gas formed stars? How representative the brightest early sources are of the wider population? How strongly pre-Webb simulations underestimated luminosity or structural maturity? Whether some early disk-like systems are genuinely rotation-dominated in the strong sense. How best to model the earliest stellar populations and their spectra. How much early chemistry demands revisions to standard formation scenarios. These are serious scientific tensions, not clickbait inventions. They are exactly where active research lives. They do not mean physics is broken, but they do mean the old pace of cosmic development may have been too conservative in important respects. #### What remains speculative or overblown? The claim that Webb disproved the Big Bang. The claim that cosmology has collapsed. The claim that early galaxies logically cannot exist under any form of standard physics. The claim that every bright candidate is a confirmed impossibility. The claim that one surprising structure proves the universe is fundamentally different from the broad framework we use now. These are overreaches. They thrive because surprise is monetizable. But they blur the real, subtler revolution. A telescope can transform our understanding without delivering a cartoon catastrophe. And if we are honest, the subtler revolution is usually the more lasting one. The Webb story is not about a clean rebellion against all existing theory. It is about stress testing one of the most sensitive eras in cosmic history and revealing that the universe may have learned to build itself with far more speed and efficiency than we had comfortable stories for. This is why the scientific mood around Webb is so fascinating. It is a mix of exhilaration and self-correction. Some claims soften. Others strengthen. Some early estimates are revised downward. Yet the general sense of tension remains because the early universe continues to refuse the simple, naive, slow-growth narrative. That is the difference between hype and discovery. Hype wants one shocking headline. Discovery keeps surviving revision. And once a pattern survives revision, it enters the deeper layer, the layer where science stops asking, "Is this real?" and begins asking, "What kind of universe makes this real possible?" That is where we are now. And that is where the emotional weight of this story finally comes due. Because behind the spectroscopy, the redshifts, and the simulation debates is a more human disturbance. The universe may have become structured and knowable much faster than we thought. And that changes not only cosmology. It changes the emotional meaning of the beginning. There are scientific discoveries that expand knowledge. And then there are discoveries that alter the emotional profile of reality. Webb belongs to the second category. Because hidden inside every argument about stellar mass, oxygen abundance, and early morphology is a deeper human discomfort. We have long associated beginnings with simplicity. We grant the first moments of anything a kind of innocence. A child is unfinished. A civilization is primitive at first. A galaxy, we assumed, begins dim, chemically naive, and structurally rough. Webb is not fully destroying that intuition. It is humiliating it. The early universe may have become legible, structured, and complex with unnerving speed. That should feel strange even if you are not an astronomer, because it tells you something about reality's temperament. The cosmos may not be the patient, slow-blooming thing our metaphors prepared us for. Under the right conditions, it may rush toward complexity. It may make use of available matter, radiation, and gravity with startling ambition. It may turn darkness into order on timescales that, from a human conceptual standpoint, feel almost rude. And there is something psychologically destabilizing about premature order. Chaos arriving early is easy to imagine. Violence arriving early is easy to imagine. But recognizable order, chemistry, and maturity arriving early force a more intimate revision. They suggest that the universe was not groping toward itself as hesitantly as we thought. Maybe it was eager. I do not mean conscious. I mean dynamically impatient. The laws plus the initial conditions may have been enough to produce visible complexity faster than our storytelling instincts allowed. And once that possibility is admitted, the beginning of the universe stops feeling like a distant nursery and starts feeling like a compressed rush of becoming. This changes how we imagine ourselves too. For a long time, it was emotionally easy to think of the cosmos as having taken immense ages to produce anything like structure, much less life and mind. That picture gave human existence a certain dramatic scale. But if galaxies were already chemically alive and dynamically active shockingly early, then complexity itself may not be as chronologically delicate as we like to imagine. The universe may begin building the prerequisites for later richness very quickly once the right doors open. That is both awe-inspiring and humbling. Awe-inspiring because it makes the cosmos feel fertile. Humbling because it reminds us that our intuitions about what should take a long time are often provincial. There is also a more subtle emotional injury here. We tend to equate darkness with ignorance and ignorance with undevelopment. But deep space keeps teaching the opposite lesson. Something can be hidden from us not because it is empty or primitive, but because light took too long to arrive. The young universe was not necessarily simple while we were blind to it. It was simply out of reach. That means our ignorance of cosmic dawn was not innocence. It was delay. And that realization gives Webb a haunting character. It is not merely discovering new objects. It is receiving old evidence late. It is showing us that while the universe seems silent from our vantage, it may already have been building vigorously in the dark. Webb is not seeing monsters but premature order. That line may be the deepest summary of this whole story. Because monsters would be easier. A monstrous universe is narratively generous. It gives fear a face. It gives anomaly a shape. Premature order is more disturbing because it suggests not that the universe is broken, but that it has been more competent than we were ready for from the very beginning. And if that is true, then perhaps the real shock of Webb is not that the sky contains impossible things. It is that the sky contains a beginning with less hesitation than ours. A universe that assembled itself with unnerving speed is not a fantasy. It is a possibility now written into serious scientific tension. And once you absorb that, the darkness between the stars starts feeling different. It no longer feels like a slow empty prelude. It feels like withheld evidence of a history that may have outrun our imagination long before our species existed to ask about it. Which leaves us with the last question. What, finally, did Webb detect? Not in the headline sense. In the deeper sense. What did it force us to see about the character of the universe? Let us gather the pieces carefully. James Webb did not discover a magical object that should not exist under any conceivable physics. It did not prove the universe is nonsensical. It did not reduce modern cosmology to rubble in one spectacular blow. What it did may be more unsettling than that. It began revealing a recurring pattern in the early universe, a pattern of systems that appear earlier, brighter, more chemically evolved, or more structurally organized than many prior expectations had comfortably allowed. Some of those first impressions have been softened by better analysis. Some candidate extremes have become less extreme. Some headlines were too loud and too fast. But after the corrections, the deeper unease remains. The early universe keeps turning out less primitive than expected. That is not a slogan anymore. It is the core revelation. Webb has shown us that deep space is not merely distant emptiness. It is a delayed archive of cosmic youth. And when we finally gained the ability to read that archive properly, we did not find a simple nursery. We found a cosmos already busy with rapid star formation, early chemical processing, environmental transformation, and perhaps even the first signs of recognizable order. The impossible, in this context, does not mean lawless. It means the timeline itself may have been too conservative. Maybe galaxies assembled light faster. Maybe stars formed more efficiently. Maybe heavy elements appeared sooner. Maybe reionization began with more intensity. Maybe some systems organized their gas and angular momentum faster than our habits allowed. Maybe the beginning of visible cosmic structure was not gradual enough to satisfy our metaphors. The universe may have grown up too fast. That is the sentence Webb has placed on the table. And it changes how we think about cosmic history. Because once the early universe becomes more ambitious, everything downstream has to be reconsidered in tone, if not in total framework. The origin of galaxies becomes less like a slow tutorial and more like a compressed improvisation under extreme conditions. The first luminous systems become less like fragile candles and more like fierce engines of transformation. The dark ages no longer feel like a long emptiness. They feel like the silence before a very rapid build. This is why Webb matters philosophically, not just observationally. It is teaching us that origins are not always simple. The beginning of a thing may already contain surprising speed, pressure, and competence. The first chapters of the cosmos may have been less childlike and more front-loaded with consequence than we imagined. There is something deeply human in resisting that idea. We want beginnings to be obvious. We want complexity to arrive on a timetable that feels narratively fair. We want the early universe to be primitive because that makes our later universe feel properly earned. But nature owes us none of that dramatic pacing. It gives us law. Initial conditions. Matter. Radiation. Gravity. Expansion. And from those ingredients it may produce visible complexity faster than our intuition can emotionally metabolize. That is the real reason Webb feels disruptive. Not because it found impossible things in the fairy tale sense. Because it found a universe whose developmental tempo may have been stranger than the stories we told about it. A universe that does not wait politely to become interesting. A universe that may begin enriching itself, clearing its own fog, and building recognizable forms almost as soon as the conditions allow. A universe in which darkness does not mean immaturity. A universe in which hiddenness was never emptiness, only latency in the arrival of evidence. And perhaps that is the deepest lesson of all. Deep space may be hiding not violations of law but a timeline more aggressive than our theories expected. Webb is not looking at monsters. It is looking at premature order. That order is still under investigation. Some of it will be revised. Some of it will be modeled better. Some of it will look less shocking once theory catches up. That is how science breathes. But even when theory catches up, the emotional truth will remain. The universe we are discovering is not calmer than we thought. It is not simpler than we thought. And it may not have been as patient as we thought. Its first visible structures may have arrived with unnerving urgency. So when people ask what James Webb just detected that should be impossible, the most honest answer is this. Not one impossible object. Not one fatal blow to physics. Not one neat revolution. It detected evidence that the young universe may have assembled itself with astonishing speed, enough speed to force us to rethink how quickly light, chemistry, and order can rise out of the deep dark. And that is, in its own disciplined way, more unsettling than the headline ever was. Because a universe that breaks the rules is easy to dramatize. A universe that followed the rules and still grew up too fast is harder. Harder to simplify. Harder to forget. Harder to trust with the old metaphors. The night sky used to look old because it was distant. Now it also looks dangerous to expectation. And once you understand that, you never quite see darkness the same way again.